Greetings, this is Professor Roman. We will continue our discussion of linear functionals. First of all, linear functionals, of course, are defined on vectors. If f is a linear functional on V, then f is defined on the vectors in V. But as we have done before with linear maps and functions in general, we can define f on subsets of V. F of x is simply the set of all f of V, where V ranges over the subset x. So let's let x be a non-empty subset of a vector space V. The annihilator of x, denoted by x with a superscript 0, and I'm just going to read this x0, is the set of all linear functionals on V that send every vector in x to 0. So this is the definition in symbols. x0 is the set of all linear functionals on V such that f of x is the singleton set 0. The term annihilator is a nice descriptive term. A linear functional annihilates a vector if it sends it to 0. So that's where the term annihilator comes from. And it's quite easy to see that the annihilator of a subset is, let's say a non-empty subset, is the same as the annihilator of the span of that subset. If a linear functional annihilates x, it annihilates any linear combination of vectors in x. If V is a vector space, S is a subspace, and we take any complement of S, we can decompose V into a direct sum. It would seem reasonable that the annihilators of the subspace S are essentially just the linear functionals on T. Of course, I have to say essentially because the linear functional on T is not a linear functional on V. But the point is, if we have a linear functional on T, we can extend it to a linear functional on V by sending every vector in S to 0. In other words, we get an annihilator of S in that manner. So to do this a bit more formally and precisely, consider the restriction map that sends any annihilator of S. Now remember, that's a linear functional on V that annihilates S to a linear functional on T by just restriction to T. Restrict the domain to T. There's no need to restrict the codomain. It's already the base field. We get a legitimate linear functional on T. Restriction, as we have seen before, is linear. And any linear functional f on V is completely determined by the two restrictions, restriction to S and restriction to T. And so any a linear functional that annihilates S sends everything in S to 0. We've already said what it does to S. All we have to do is deal with what it does to T. In other words, any linear functional in S naught is completely determined by its restriction to T. Put another way, this restriction map is injective. If we know the value of f at t, on t I should say, then we know f, because f annihilates s. So we know everything about f. We know what it does to t, we know what it does to s. But this is also a surjective map, because any linear functional on t, as I mentioned before, can be extended to a linear functional on v by sending everything in S to 0. So this is in fact an isomorphism. So here's the theorem. The restriction map is an isomorphism, and it maps S naught to T star, so these guys are isomorphic. The linear functionals on V that annihilate S are essentially the linear functionals on T. So if V is finite dimensional, then the dimension of S naught is equal to the dimension of T star. That would be the case even without finite dimensionality. But in the presence of finite dimensionality, the dimension of T star equals the dimension of T. So the dimension of S naught, the annihilator of S, is equal to the dimension of any complement of S. Here is a summary of results on the annihilator, and actually some additional results as well, properties of the annihilator. So V is a vector space, and S is a subspace of V. Taking the annihilator is order reversing. If M and N are non-empty subsets of V, if M is contained in N, then N naught is contained in M naught. If S and T are subspaces of V, then the annihilator of the sum is the intersection of the annihilators, and the annihilator of the intersection is the sum of the annihilators. If V is a direct sum of S and T, then the restriction map is an isomorphism. This is what we just got through dealing with. And so these are isomorphic, and these dimensions are equal. So I'm going to leave the proof of the first part to you for practice. The third part we've already proven, so we just have part 2 to deal with. Well, it's clear that if a linear functional annihilates S plus T, then it annihilates S, and it annihilates T, which means this is contained in this. Where'd that go? Well, it would be here. But the reverse inclusion is also true. If F annihilates S and F annihilates T, then it will annihilate any sum of vectors of the form little s plus little t. So that takes care of this first equality. The other equation is a bit more of a strain. We do know that S naught is contained in S intersect T naught because of the reversal of inclusion. That was part 1, order reversing. And similarly, T naught is contained in S intersect T naught. So this sum is contained in S intersect T naught. It's the reverse inclusion that is a little testy. Perhaps there is a better proof, or at least a shorter proof. So suppose we take a linear functional that annihilates the intersection. we have to show, call it F, we have to show that F is the sum of an annihilator of S and an annihilator of T. Well, we can start by taking the subspace S intersect T and finding, since that belongs to S, it's also a subspace of S, so we can flesh it out, so to speak. We can decompose S into S intersect T, direct sum with S a complement S prime. And we can do the same for T. T is, excuse me, T is S intersect T, direct sum with T prime. Now, the key observation is that the sum S prime plus S intersect T plus T prime is a direct sum. So, to see this, we have to check for strong essential disjointness, or equivalently that the zero vector has no non-trivial expression as a sum of vectors from each of these subspaces. So let's say S prime plus X plus T prime is 0. S prime comes from here, X from here, and T prime from here. Then S prime is negative X minus T prime, which belongs to T. So S prime belongs to both capital S prime and T, but the intersection of these two is trivial. And so S prime is 0. So that means that X plus T prime is 0, and that implies that both X is 0 and T prime is 0. So this is a direct sum. Now we can expand W to express V as a direct sum of W with a complement of W. This is W here, so call it U. Now we can define linear functionals on V by saying what they do to each of these 4 subspaces. G restricted to S prime is F. G restricted to S intersect T is 0. G restricted to T is 0. G restricted to U is F. And we can define another map, H, another linear functional, sending S prime to 0, the intersection to 0, T, on T it acts the same as F, and on U it's 0, and so G annihilates T, so it's in T naught, H annihilates S, so it's in, H annihilates both S prime and S intersect T, so it annihilates all of S, and so it's in S naught, and when you add these two together, you get F. Okay. Now let's ask a question. Suppose that tau is a linear map from V to W. How would you use tau to turn a linear functional f on W into a linear functional g on V? what we're looking for then is a map from W star to V star. Note the reversal in the direction here. Well, the whole story is in this picture. All you have to do to turn a linear functional from W to F into a linear functional from V to F is to pre-compose tau by, pre-compose F by tau. In other words, place tau in front of F, because then F circle tau has domain V. So if I call that G, F circle tau is composition of linear maps, so it's linear, but now it goes from V to F. It's a linear functional on V. So by putting tau in front of any linear functional from W to V, we get a linear functional from V. Did I say that right? From W to F, we get a linear functional from V to F. This pre-compose by tau is a map, and we will denote it by tau with an arrow superscript. There are many notations for this, but I like this one because I think it helps remember the phrase, put tau first. So tau arrow of F is F tau, or this is F composed with tau, but it's commonplace to denote composition just by juxtaposition in this context. Okay. So in particular, for any vector V, tau arrow F applied to V, you just apply tau first to V, then you apply F. So, definition, the pre-compose by tau map, tau arrow, maps W star to V star. I probably, since this is a definition, I should say let tau be in L of VW. So I'm going to add that. The pre-composed by tau map, tau arrow, maps W star to V star, and it's defined this way, or in words, place tau first. And this is called, tau arrow is called the dual map of tau. And the thing to remember is tau arrow means apply tau first. So here is an example. Tau maps F3 to F2, defined this way. Tau arrow of E1 star. Remember, tau arrow now maps F2 star to F3 star. So F2 has dual basis, E1 star and E2 star. So if I can find these values, then of course I know tau arrow on everything. So tau arrow of E1 star applied to an arbitrary vector in F3. First thing you do is you apply tau first, and tau of xyz is given right here. And what does E1 star do? It picks out the coefficient of, or component of, E1 in this vector. That's the first coordinate, x plus y plus z. And then tau arrow E2 star of v, when you get to here you have 2, E2 star, it just picks out the second component. So these two equations tell you uniquely define tau arrow. Some properties of the dual map. Taking the dual of a map is a linear process. If tau and sigma are linear maps from V to W, A and B are scalars, then applying the arrow to a linear combination is the same as applying the arrow to tau and sigma separately and then taking the linear combination. If the maps sigma and tau are compatible with composition, then tau sigma arrow is sigma arrow tau arrow. And note the reversal. Just as it's the same situation if we were taking inverses for invertible maps. Okay. If tau is an invertible operator, then tau inverse arrow is tau arrow inverse. So I've left part of this for you. Actually, I think I'm going to leave all of the proof for you. It's not very difficult, and it would be good practice. Dual maps are connected with annihilators through their kernel and image. So if tau is a linear map from V to W, the kernel of tau arrow of the dual map is the annihilator of the image of the original map. And the image of the dual map is the annihilator of the kernel of the map. So if you want kernel or image of the dual map, switch from kernel to image or image to kernel and take the annihilator. Perhaps that's the best way to try to remember these formulas. Okay. Swap kernel for image, swap image for kernel, then take the annihilator. As to the proof, part 1 actually is a bit simpler than part 2. The kernel of the dual map is the set of all linear functionals on W that are sent to 0 by the dual map. Those are the linear functionals for which precomposing by tau is the 0 map, or in other words, F applied to the image of tau is the 0 subspace. In other words, the linear functionals that annihilate the image. For part 2, if F is in the image of the dual map, there's a G in W star for which F is dual map applied to G, or in other words, G tau. Well, then F annihilates anything that tau annihilates. So you apply tau first, you get 0, F has annihilated it. So the image of tau star is at least contained in the annihilator of the kernel. It's the other inclusion. It's a little bit testier. It's not too bad. Let F be in the annihilator of the kernel of tau. We want to show that there is a G in W star for which F is tau is the tau arrow of G, or in other words, G tau. Or, put another way, F applied to any vector is G tau, that vector, for all vectors V and V. Okay. Well, this equation, we're looking for G. This equation is an attempt at a definition of G on the image of tau. It tells us what G needs to do to the image of any vector, or in other words, the image of tau. The question is there such a G? Is there a linear functional G that has this behavior on the image of tau? The first problem is that G, if we tried to define G by this equation, is it well defined? A vector in the image of tau may be the image of several V's here. And we have to get the same thing out of this to be well defined. So, if tau V is equal to tau W, we have to show that G of tau V equals G of tau W. But it's all right here. If tau V equals tau W, then V minus W is annihilated by tau in the kernel of tau, and therefore it's annihilated by F, because anything annihilated by tau, where did it go here, is annihilated by F. So F of V equals F of W, and so G of tau V equals G of tau W. That makes G, this equation defining G makes G well defined on the image of tau. As for linearity, it's all right here. It follows essentially from the linearity of F and tau. So it remains only to extend. So we've got we've got a well-defined linear map, G, on the image of tau, which is a subspace of V. All we have to do, a subspace of W. All we have to do is extend G linearly to all of W. And that concludes the proof here. In the finite dimensional case, both tau and its dual map can be represented by matrices. So it is natural to wonder how these matrices might be connected. Suppose that, I should also start this by saying let tau be an L of VW. Okay, so let's let B be an ordered basis for V and C be an ordered basis for W, and take the dual bases. We want to compare the matrix representation of the dual map, tau arrow, with respect to the dual bases. Now, since we're going in the opposite direction, now we're going from W to V, the matrix representation, the first basis is C prime, the second basis is B prime. We want to compare this matrix to the matrix representation of tau with respect to B and C. So we have to pull apart these matrices. We need to examine the individual entries. So we'll start with the simpler matrix that we're more familiar, more comfortable with, let's say. And let's say the coefficients, the entries of this matrix are aij. Now, the jth column of this matrix, as we know, is the c-coordinate matrix of the image of the jth basis vector. And let's say it looks like this then. Okay. This is the jth column. So tau of uj is given by these c coordinates. So the c vectors are v1 through vm. So we have this linear combination. Therefore, the ith entry in here, which is aij, is the ith coefficient here, coefficient of vi, and we can pick out the coefficient of vi by applying vi star, the dual basis vector. So aij is vi star tau uj. Well, we can do the same analysis for this other matrix, the matrix representation of the dual map. The jth column will look like this, and so the dual map applied to Vj star is this linear combination of the dual basis B star, and to pick out the ith entry here, we apply this to ui. So we apply this linear map to ui, we get this, Vj star tau ui. Now it's time to compare. And if you look at these two, all you have to do is swap I and j, and you'll go from here to here. So aij is bji. Well, in other words, these two matrices are transposes of one another. Okay. Not bad. We started with a question, we did some analysis, we looked carefully at these two matrices, at their individual entries, and we discovered a very simple relationship between them. If tau is a linear map from V to W, finite dimensional vector spaces, B and C are ordered bases with their dual bases, then these two matrices are transposes of one another.